Okay, let's jump right into this explainer of Lecture 16 by Skip Unai and demystify the completely powerful and honestly super fun world of C++ bitwise operators. Look, if you've ever felt a bit intimidated by the idea of manipulating data at its absolute most fundamental, microscopic level, you are definitely not alone. But today, we're going to break it all down. We're going to make it visual and show you exactly why understanding these operators is a literal game changer for your coding efficiency and for your confidence in technical exams. We have a packed workshop today, so here's our roadmap. We'll cover logical versus bitwise operators, the core operators, and, or, and XOR, the bitwise NOT, shift operators and overloading, some amazing math shortcuts, and finally, how to use all this to ace your coding interviews. All right, let's kick things off with section 1, logical versus bitwise operators. So let's clear up a really common roadblock right out of the gate, the difference between macro and micro evaluations. It is incredibly easy to confuse logical operators with bitwise operators, mostly just because they look so similar, but they actually perform entirely different jobs. This comparison brilliantly illustrates the contrast. If you look at the logical double ampersand, it's checking high-level conditions. It looks at a whole statement and basically asks, hey, is this entire thing true or is it false? But the bitwise single ampersand, that operator pops the hood of your variables. It doesn't care about the high-level stuff. It gets its hands dirty by looking at the actual, raw ones and zeros that make up your data, comparing them bit by bit. Moving right along to section 2, core operators, and, or, and XOR. To really see exactly how these tools manipulate data, we're going to use a controlled laboratory environment. We've got two constant variables, a equals 5 and b equals 3. By keeping our inputs totally consistent, we can perfectly observe how each operator uniquely transforms the data. Let's start with the bitwise AND operator. Looking at our variables in binary, our 5 is 0101 and our 3 is 0011. So the crucial point for bitwise AND is this. If even a single bit is 0, the output is 0. Both bits literally must be a 1 to output a 1. Look at the vertical alignment. First bits, 0 and 0 gives 0. Second, 1 and 0 gives 0. Third, 0 and 1 gives 0. But those final bits on the right, they're both 1s, so our output is a 1. The resulting binary is 0001, which is just the decimal number 1. Let's move over to bitwise OR, which is represented by that vertical pipe symbol. Here, the rule shifts dramatically. For bitwise OR, if at least one bit is a 1, the output is going to be a 1. It's way more inclusive. Looking at our same numbers, 0101 and 0011, let's compare them vertically again. Aside from that leftmost column where both are 0, every single other column contains at least one 1. Therefore, our result just populates with 1s, giving us 0111. Translate that back to decimal, and boom, we get 7. Okay, now look really closely at the bitwise XOR, represented by the caret symbol. XOR stands for exclusive OR, and the rule here is strict. Matching bits output a 0, but differing bits output a 1. If they're the same, whether that's two zeros or two 1s, the output is 0. Let's look at our bits again. First column is 0 and 0, so they match, output is 0. The second is 1 and 0, they differ, output is 1. Third is 0 and 1, they differ, output is 1. The last is 1 and 1, they match, so output is 0. We are left with 0110, and that binary sequence equals the decimal number 6. So here is a super clean summary grid of those three core operators manipulating our base variables. Notice how the exact same input, 5 and 3, yields entirely different results, 1, 7, and 6, simply based on the bitwise rule being applied. It just perfectly showcases the precise control you have over your data. Let's dive into section 3. Bitwise NOT, also known as the flipper. Unlike AND, OR, and OR, which obviously require two operands to compare, this next operator works entirely solo on just a single variable at a time. The bitwise NOT operator, represented by the tilde symbol, performs what's called a ones complement. It doesn't compare a single thing. It simply inverts. Every 0 becomes a 1, and every 1 becomes a 0. It is the ultimate digital flipper. Let's see it in action, shall we? By applying the NOT operator to our trusted variable 5, the binary sequence 0101 instantly flips. Zeros become 1s, 1s become 0s. We're instantly left with 1010. If you calculate that binary value, it equals 10 in decimal. It's just a remarkably fast way to invert binary data states. Next up, section 4, shift operators and overloading. Now we move on to shift operators, which actually come with a pretty surprising plot twist in the C++ universe. You've almost definitely used these symbols before, but perhaps not in the way we're about to discuss. This brings us to a prime example of operator overloading. Operator overloading is this fascinating concept where the compiler is actually smart enough to look at the context surrounding a symbol to figure out what job you want it to do. It's like one person working two very different jobs depending entirely on where they're standing. This perfectly proves how the exact same symbols can moonlight doing two completely distinct jobs. With cout followed by two less than signs, you know this as a stream output operator, used to print text to the screen. But when placed between two integers like 5 and 1, those exact same symbols totally transform into a bitwise left shift operator. The compiler understands the context and just executes the correct operation seamlessly. Let's get into section 5, multiplication and division shortcuts. So you might be wondering, why should I even care about physically shifting binary bits left or right? Well, because these operators act as incredible mathematical cheat codes for your computer's processor. Let's look at the mechanics of the left shift operator, which is pretty universally known in programming as the multiplication by 2 shortcut. If we take our binary 5, 0, 1, 0, 1, and shift it left by 1 position, everything physically moves to the left. The leftmost bit drops off completely, and a 0 is naturally added to the newly empty space on the far right. Our 0, 1, 0, 1 becomes 1, 0, 1, 0. We started with 5, and we ended with 10. We effectively multiplied by 2 without ever actually invoking a standard multiplication operator. And conversely, right shifting acts as division by 2. If we take our 10, 1, 0, 1, 0, and use the right shift operator to move it right by 1 position, everything slides to the right. The rightmost bit drops off the edge, and a 0 fills the empty space on the left. The 1, 0, 1, 0 reverts perfectly back to 0, 1, 0, 1. Our 10 has been divided by 2, bringing us right back to 5. But hold on, let's look at a tricky scenario here. What happens if we right shift an odd number, like 5? The inside scoop here is that bitwise right shift division yields the integer floor value. If we right shift our 5, 0, 1, 0, 1, the rightmost 1 just drops off and we get 0, 0, 1, 0, which is 2. Now wait a minute, 5 divided by 2 is 2.5, right? Well, yeah, but because we are dealing with bits and integers, the decimal is totally discarded. It always rounds down to the integer floor value. Understanding this precise output is a massive advantage. Finally, section 6, acing your coding interviews. Understanding these precise outputs, knowing exactly how bits drop off and how integer floor values are calculated, is absolutely vital for competitive programming and technical interviews. When an interviewer asks you to optimize a mathematical function, utilizing shift operators instead of standard arithmetic really demonstrates a deep foundational understanding of how C++ handles data in memory. You now have the tools to look right past that surface-level logic and manipulate the very building blocks of your data. I'll leave you with this question to ponder so you can take these powerful shortcuts into your next coding challenge. The next time you're faced with a complex division problem that only requires integer outputs, how much processing time could you save by shifting the bits instead of calling traditional math functions? Keep that in mind and keep practicing those bits.